the emerging area in computing field. Before getting into the session, I must thank the management of Atal institutions, Atal FTP officials, principals, sir, Dr. Panasaran sir and coordinates of Atal FTP program for providing this wonderful opportunity to present the session in quantum machine learning models. This session has several discussions. It is I used to introduce about quantum computing, then key principles associated with quantum principles and quantum computing. Then I will introduce about quantum gates, which is completely different from digital logics. And I wish to explore about quantum computing technologies and the association with data science machine learning to improve the speed up and optimize the machine learning task. Then I wish to tell about the algorithms which is associated with machine learning. It is we realize the marriage between quantum computing and machine learning nowadays. And I will discuss about challenges, case studies associated with quantum machine learning. Finally, I will give some demonstration with the help of PennyLearn tool. It is how to work with quantum computation. There is simulation environment by using Python programming language. And also I will give hands-on experience in MLOps. That is how to develop MLOps pipeline by using Python programming language with the conclusion. So quantum computing is completely different from digital computing, which relies on quantum mechanics. There are several key characteristics principles associated with quantum mechanics. I wish to tell about those things. It makes use of key principles such as superposition and entanglement to improve the process the data, improve the computation and process the data. Actually, quantum is the smallest unit of phenomena which involves quantum mechanics. We deal with processing at a subatomic level. That is even smaller than an atom. We use key principles associated with the quantum mechanics, such as superposition, entanglement, coherence, and interference. The main aim of quantum computing is to process or solve the problem, taking advantage of a phenomena that occur at a subatomic level. So, like digital logic, we deal with the zeros and ones. Here in quantum computing, we usually deal with the qubit. Okay. So, in digital logic, we use zeros and ones. No, either we have zero state or one state. We represent two kind of data in terms of two values. But in quantum bit, we use another state called superposition state. There is state between 0 and 1. This is a concept again quantum computing. As I said already, there are key principles of quantum computing. Main principles are superposition and entanglement. I will explain one by one. Other principles which is used to enable quantum computing are decoherence and interference. These are the key principles. Actually, superposition means, so apart from zero state and one state, we have another state called that is superposition state, that is state between 0 and 1, which is measured by using the probabilistic value. Okay. So by using the qubit and superposition state, we can realize several possibilities of states, so that we can to make the advantage, use the advantage of those things, we can perform several computations, complex computations in a quick way. So we have several complex and multidimensional computation spaces, so which can be used in optimization purposes, and in evolution algorithm also we can use quantum computing to explore several set spaces, large set spaces. So there is advantage of using superposition state. Next one is to completely explain the concept, that is illustrate the concept of superposition. there is an experiment called Schwanger's cat thought experiment. Here there is a closed box. In the closed box we keep cat. Okay, actually it is a live condition, and also we have poisonous gas and a radioactive atom. Okay, so in a hypothetical scenario, a living cat is placed inside a steel box. Along with the cat, the box contains a sealed vial of poisonous and a radioactive atom. The atom is exactly has a 50% chance of decaying within 1 hour. If it is decayed, means the cat will be dead person. Okay. If it is not decayed, means the cat will be live state. So there is a possibility of, there is a 50% possibility of death state and live state. Okay. So this is the cat experiment, Schwanger's experiment. So in a similar way, superposition state, there is a possibility of having the 0 state or 1 state. Okay. So possibility means probability. Okay. There may be 30% of probability of 0 state, or remaining means 70% of possibility of live state. I mean 1 state. So we have, apart from 0 state and 1 state, we have possibilities of probabilistic value of 0 state and 1 state. There is a superposition state. So this is the concept behind superposition. And there is another key principle, entanglement. There is we have several qubits in a quantum computing environment. So we can associate or link one qubit with another qubit through entanglement principles. So we can communicate. One qubit may be able to communicate with another qubit through entanglement. For example, in a XOR logic, we have two kinds of, consider you have 2 bits and you wish to process the data, means there should be a relation between 0 state and 1 state. Okay. Otherwise, we can't be able to get the result for XOR gate. So the relation between the 0 state and 1 state, which is achieved by using the entanglement principle. Okay. It is quantum entanglement. So entanglement is the ability of qubits to correlate or associate their state with other qubits. So one qubit can be associated with the other qubit through entanglement. Next one is interference. Actually, interference is the basic engine of quantum computing. So because we are dealing the quantum computation in terms of that is subatomic level now. So one atom may be communicate with another atom. So atom will generate some waves actually, which there is an interference actually. Because of interference, we have several states. We can achieve several states. So there is one key principle that will actually interference state is used to enable the quantum computation, and also it will make the qubit to reach to a several state. There is a important principle in quantum computing. Next one is decoherence. So while subatomic level, if one qubit may be able to communicate with the other qubit, means there may be some interference. Okay, so maybe one qubit may be able to available in a superposition state. Okay, I mean quantum state. Sometimes it may not be in quantum state. If the qubit may not be in quantum state, means that we call as a decoherent state. At the particular moment, if you are failing to achieve the that is quantum state, means you may lose the data. Okay, there is a key drawback of quantum computing. So there is another principle. So being a researcher, quantum researcher, we need to reduce the decoherence. Next one is parallelism. Since we are having another state, that is superposition state, we can achieve the quantum parallelism. So in a parallel environment, we have several multipliers, several processors which will solve the problem parallelly to achieve to speed up the process. So in a similar way, by default, quantum computing, in quantum computing, we have several qubits. Each qubit in several states, so that we can achieve the parallelism. So with the help of quantum computing, we can achieve the parallelism easily. So there is a difference between classical computation and quantum computation. So in classical computation, we process the data one task at a time. In quantum computation, since qubit have maybe in several states, so one qubit process the particular data means maybe another qubit process the data in a different state. Okay, so we can achieve the parallelism. For example, suppose we have to evaluate the function f of x for the input, for several inputs like 0, 1, 2, 3. Actually, classical approach, what we do is we evaluate the functions individually by passing the values f of 0, 1, 2, 3 and all. But it requires separate evaluation, function evaluation. That is by using sequence evaluation, we can solve that problem. But in quantum approach, we have qubits which is in the superposition state. Okay. So, for example, we can have x values as different state, and each value, that is x values, pass into the different qubit. Okay. So that parallelly we can evaluate the function value, that is f of x value, to speed up, to improve the speed up. Okay. And also we have another feature called quantum tunneling. So, for example, this is mainly used in application problem. Okay. So, mainly in application problem, if you should, for example, consider I take an optimization algorithm called machine learning algorithm. So, in stochastic gradient optimization problem, we try to minimize the errors. To achieve the, to reduce the error, we try to achieve the global optimum level. So sometimes if we use basic approach means we can lead to a local optimum, local minimum. So, but I wish to achieve the global optimum, that is global minimum value. So for this situation we can use quantum tunneling. So quantum tunneling does not, for example, consider you have a mountain. Okay. So if you are using classical mechanism means just flip up the that is area and reach the local minimum. Okay, it takes more amount of time. If you use quantum computing means we can explore the global optimum, that is global minimum, quickly by using the quantum tunneling method. And it is used in high fidelity measurements, but it is slower than the superconducting qubit. Next one is quantum dots. Quantum dots is a smallest semiconductor that captures a single electron and uses it in a qubit. There are several sources of qubits. Another one is photons. We can use photons as a qubit, so which are individual light particles. Can be used to make qubits and then do quantum information across long distances. Okay. So these are the sources of qubits. So there is quantum computer manufacturing, making use of these kind of technologies to build a qubit. So there is I already told about the difference between quantum computing and classical computing. In nutshell, I can say classical computing uses several multiprocessor and multipurpose computers make use of digital devices which involve zeros and ones. And quantum computing is used by the quantum mechanics based quantum computing as well, and it processes information in terms of 0, 1 and superposition of 0 and 1. And it processes data with quantum logic by using interference to solve problems. So further differences I wish to tell. So in classical computing, we do perform any computable task using a programmable computer. But in quantum computing, we are using the quantum algorithms, which is qubit based. The building block of digital logic is zeros and ones, but in qubit the building block is 0, 1 and superposition of 0 and 1. And the nature of state is discrete, but in quantum computing we have quantized state. The memory representation, in terms of memory representation, is explicit in classical computing. Consider if you have n bits means it stores exactly 1 of 2 4 n possible states at a time. But in quantum computing we have exponential state. If you have n qubit means we store quantum state with 2 power n complex states. Okay, there is a difference between classical computing and quantum computing. Hardware model is classical computing makes use of one Neumann architecture, but in quantum computing making use of quantum gates and quantum cycles and measurements. In terms of scope, classical computing handles a variety of tasks such as simulations, and we can do data processing, solve AI problems and so on. But in quantum computing, we use quantum speed up tasks like sorting, searching and so on. And also we can perform quantum machine learning. Okay. Next, determinism. In terms of determinism, classical computing is a deterministic one, but quantum computing is a probabilistic one. We have several operations associated with classical computing like Boolean algebra operations like AND, OR, NOT, XOR. But in quantum computing, we can perform linear algebra operations. That is data, qubits are represented in terms of unitary matrices, so which is completely different from the digital logic. And also in classical computing, we have physical principles such as which obey the Ohm's law and the Kirchhoff's law. But in quantum computing, we deal with quantum mechanics such as superposition, entanglement, unitary evaluation, measurement. So these are the primary difference between the quantum computing and classical computing. As I said already, like digital gates, we have quantum gate. Okay. So in place of NOT gate, in digital logic, we have NOT gate here. Okay. So, but it is represented by using the block sphere. Okay. We represent the NOT gate in terms of unitary matrices, completely different. For example, a classical NOT gate usually flips 0 to 1 and 1 to 0. Here also we have quantum computing, also we have NOT gate. This quantum X gate. It also called as poly X gate. Okay. We represent in a unitary matrix. We represent actually the zeros and one state in terms of unitary matrices. Okay. This represents 1. This represents 0. Okay. So if you apply, that is flip operation means, for example, consider initially you have 0 state. So you should multiply this x value with the state 0. Actually in vector space 0 is represented as 1, 0. If you multiply, if you perform tensor product between this matrix and this matrix, you will get 0, 1. This is 1. When you apply, consider x, x is the actual matrix. Here we have 1. So 1 is represented as 0, 1. If you multiply, perform tensor product between this vector and 0, 1 means you will get 1, 0. Okay, there is a difference between the classical gate and poly X gate, quantum gate. So if you are flipping means, for example, we have 0 state and 1 state here. Consider this is 0 state and this is 1 state. Flipping means this vector space will come down. Okay. So consider you have in 1 state. If you still perform a poly X gate means this vector space will come up. Okay. This is the quantum NOT gate. Okay. As I said already, consider we have X matrix representation, we are representing as X. To perform flipping operation means 0 usually represented as 1 0. Okay, in vector matrix. Consider graph here. So here 0 means 1 0. So x-axis 1. So x-axis value is available as a p.
So this value is 1 and y value in a particular moment is 0. So that is why we represent as 1 0. Okay. So if it is 1 means y axis maybe our set peak value, that is value unit value is 1 and x axis 0. So that is why for 1 we represent 0 1 in a unitary matrix. Okay. So when you apply tensor product with x, you will get, for example, you multiply these two matrices, you will get 0 1. So this 0 1 means there is a value of quantum bit 1. So when you apply tensor product between x and 1, you will get 0. This the representation of unitary matrix representation of 0 is 1 bit. In a similar way, we have other kind of gate, that is identity gate, just nothing actually. So it ensures no change in the qubit state. Okay. So it is at a side do nothing operation, which is representing identity matrix here. It is also unitary matrix. So the applications of non-gate, quantum non-gate is a basis for building the quantum gates. It is used in quantum algorithm for state inversion or reflection. Next one is poly-Y gate. Actually, what it just means, it just flips as well as change the phase of the vector. Okay. So if you give 0 as a state pin, it will change to one state and also change the phases. Okay. That is the difference between the actual poly-X gate and Y gate. So state flipping also done and phase shifting also done. So after state changes and phase shifting, we have resultant unitary matrix as 0 minus I and I0. Okay. So it combines the properties of poly X and poly Z gate. Actually, poly Z gate is another gate. It's just only phase flip. Okay. It does not change the state. 0 state will be 0 state, 1 state will be 1 state, but it will phase flip. So, but if you use poly Y gate means we do change the state, 0 state to 1 state and 1 state to 0 state, as well as we can change phases. What it means, since we generate several set spaces, we can be able to achieve the optimal result. Okay. So, if you, there is a difference between quantum computation and classical computation. So, this is the applications of quantum computing. I have applied quantum computation in a particular research work. So, I will tell, I have the paper actually, I will tell how I applied encoded the chromosome and scored the set spaces and so on. As I showed already, there are other kind of gates called S gate and T gate. So, S gate what it do means, it asks a phase 90 degrees phase to the one state. If you supply 0 means no state changes happen. But when you supply 1 means just R is phase. Just shift it. As well as state changes does not happen. Just shift it around. Matrix operation is 1 0 0 I. So I means imaginary space actually. Okay. So because why it is called imaginary means we are rotating around the Z axis no. So it will goes to imaginary state. That is why it is called I. Okay. Next one is T gate. Actually it answers phase of 5/4 to the one state. When you supply 0 means no changes happen. Okay. So these are the basic gates, and by using these gates, we can generate a quantum circuits. Okay. So we can achieve the superposition, entanglement, and so on. So I have one example. It is called variational quantum circuit. Okay, in that we associate actual quantum qubits information with the Raman gate, and we can achieve the entanglement there, enable the entanglement there, okay, to reduce the loss in a quantum machine learning algorithms. Okay. So in quantum machine, I mean, why we're trying to reduce the loss in quantum machine, I mean, actually machine learning means, for example, we try in a supervised learning, we have input better and output better. After performing the there is this feed forward task. I mean, you are multiplying input vector with random weight vector, no? You will get some result. This is called actual output. That will be compared with the expected output. If there is a difference between the actual vector and expected vector means there is an error. Okay. If you say reduce the error means we use backward propagation, no? So in that situation, we are calculating the gradient. It is smallest unit of weight. Okay. Then we need to reduce that weight. Okay. To optimize the machine learning. To achieve that, we are using quantum computing. There is quantum computation only. Okay. We are not using quantum computer. We are using the quantum computation. Calculate the gradient and implementing the back propagation method, we are using the quantum computation. So this is the visual representation of phase Z gate, S gate, and D gate. If you use phase D gate means it's just shifting by 5/4. S gate means 5/2, and Z gate means 180. Okay. And the other one is controlled NOT gate. It is another one. It is mainly used to enable the entanglement. Okay. You can use CNAND gate for SR implementation, XR logic implementation. Okay. So actually, if you can change the state of a particular qubit. Okay, when control bit is 1. For example, you have input value as 0. If you still make the changes 1 means, we need to enable the control bit to 1. If it is 1 means, the changes happen. If it is control bit 0 means, no changes happen. Okay, that is called the control NOT gate. So you flip the target bit only if control bit is 1. In multiplexer we have one control bit, no? Okay, to select the particular output, we have control bit. So if you use one control bit means, it has a control bit may have a state like 0 and 1. Control bit is 1 means you will get the actual changes. Control bit 0 means no changes happen. In a similar way we have a control NOT gate. Okay. So actually control NOT gates is represented by using the unitary matrix like this. So how do you achieve this unitary matrix means? Consider we have 2 qubit which has state 0, 0. That is represented as a matrix in terms of matrix 0, 0, 0. And then we have identity matrix. If you perform tensor product over these two matrices, you will get result like this. Okay. Next we have one state. Okay. One is represented as 0, 1 here, and we multiply with the x, you will get result like this. When you add two matrices, you will get result here. This matrix is represented as C NAND gate. In a unitary matrix, C NAND gate will be represented like this. Okay. So we can achieve this matrix by performing the tensor product. Okay. So consider I have